Hi, welcome to the MKN universe. Let's explore electron backscatter diffraction. Around the lab, you'll usually just hear material scientists and engineers call it EBSD. Today, we're going to unpack exactly what this incredible technology is, where it came from, and where it's taking the future of engineering. To really kick things off, we have to look back at this fascinating little anomaly known as the P pattern. It was literally a complete lab accident, and it took scientists decades to fully figure it out. But today, well, the technology born from that anomaly is the absolute gold standard for microstructural analysis. Seriously, if you've ever flown in a commercial jet or, I don't know, even just popped open an aluminum soda can, the materials keeping you safe were almost certainly tested using this exact method. So, here's our roadmap for today's explainer. We'll start with the accidental P-pattern discovery, move into the evolution of EBSD, break down how the actual machine works, dive into the physics of Bragg's law, look at some real-world applications, and finally wrap up with the future of characterization.
All right, part 1, the accidental P-pattern discovery. Let's travel back to 1928 at the Imperial University of Tokyo. Our story starts with a researcher named Shoji Nishikawa and his 26-year-old protege, Seishi Kikuchi. They were out there exploring the brand new frontier of electron diffraction. They were firing a beam of 50 kiloelectron-volt electrons at a calcite crystal. But they didn't quite get what they expected. Instead of the usual X-ray spots they were used to seeing, they found these incredibly strange pairs of parallel black and white lines. Completely unsure of what they were looking at, they basically just dubbed them P-patterns, which was short for pattern of the fourth kind.
Now, these mysterious lines eventually became known as Kikuchi lines. And Kikuchi's accidental discovery was absolutely groundbreaking because, well, it helped prove the wave nature of electrons. Fast forward to today, and these exact same Kikuchi lines formed the absolute fundamental building blocks of modern EBSD technology.
Moving right along to part 2, the evolution of EBSD, from rulers to CMOS sensors.
You might think a discovery like that would immediately change the world overnight. But honestly, for nearly 50 years, analyzing these patterns meant sitting alone in a dark room, manually measuring lines on a photograph with a physical plastic ruler. Yeah, not exactly fun. Looking at the timeline here, things finally got moving in 1984 when David Dingley invented live video viewing inside the microscope. Then came the huge automation revolution of 1991, which ultimately paved the way for the ultra-fast CMOS detectors we use today that can literally map thousands of points per second. And that massive 1991 leap forward, that was all thanks to a brilliant mathematical trick called the Hough Transform. Instead of forcing a human to painstakingly find and measure parallel lines, the Hough Transform mathematically turns those lines into distinct points in a completely different space. This allowed computers to automatically identify crystal orientations in absolute milliseconds. It was a real game changer that essentially gave birth to modern EBSD as we know it.
Okay, part 3, how the machine works. Let's take a look inside the modern add-on. So how does an EBSD system actually operate inside a standard scanning electron microscope today? Well, it's essentially an incredibly sophisticated add-on. If you peek inside the vacuum chamber, the very first thing you'll notice is the geometry. It looks a bit wild. The sample is tilted to a really steep angle, right about 70 degrees, and it's facing directly toward a phosphorus screen. This steep tilt is absolutely crucial. It's what allows the backscattered electrons to actually escape the surface with enough energy to hit that screen.
Once the sample is tilted, the machine fires off this rapid-fire 4-step automated process. First up, the camera captures the glowing pattern on the screen. Second, the software applies our old friend the Hough Transform to instantly spot those Kikuchi lines. Third, it takes the angles of those lines and compares them against a massive database of known structures to index the crystal. And finally, the electron beam steps to the very next pixel, mapping the entire material out, grain by microscopic grain.
Which brings us to part 4, the physics of Bragg's law and how we're creating these patterns.
To really grasp what that computer is capturing, we've got to look at the underlying physics for just a second. When the electron beam hits our sample, the electrons scatter outward in all sorts of directions. But the ones that satisfy a very specific physical rule are diffracted into these 3D cone-like structures called Kossel cones. And when these 3D cones intersect with our flat 2D phosphor screen, boom, they create this characteristic glowing bands, the Kikuchi lines, that the camera is actually looking for. And the absolute gatekeeper rule governing all of this, that would be Bragg's law. N times lambda equals 2 times d times the sine of theta. This simple, elegant equation determines exactly how and when those scattered electrons are allowed to diffract and form those costal cones in the first place. What's truly fascinating about this equation is how these seemingly simple variables dictate the exact bands the machine reads. Lambda is just your electron wavelength. And d, this is the big one. D is the actual physical spacing between the atomic planes. Because that atomic spacing is completely unique to every single mineral or metal in existence, the resulting angles of the bands act like an undeniable, totally unique fingerprint for that specific material. Let's move on to part 5, real-world applications. How are we actually reading these materials? So, why does all this matter out in the real world? Well, the only real rule for EBSD is that your sample has to be crystalline, meaning its atoms are arranged in a neat repeating lattice. We use it on metals and alloys to check the grain size in supercritical stuff like jet engine turbines. Geologists use it to understand the actual history of the Earth's crust by looking at rocks, and the tech industry, they use it constantly to check the quality of microscopic thin films inside semiconductors. It is literally everywhere around us. By the way, if you want to dive deeper into the physics of all this, these texts right here are perfect resources. Adam Schwartz and Mukul Kumar's book is quite literally known in the industry as the EBSD Bible. Valerie Randall and Olaf Engler provide hands-down the best practical guide for beginners. And Brandon and Kaplan offer a really brilliant broader look, putting EBSD in context with all sorts of other microscopy techniques. Finally, part 6, the future of characterization, focusing on high resolution and AI. You know, we are no longer just looking at basic crystal orientation anymore. We are stepping firmly into the era of 3D EBSD mapping and, of course, artificial intelligence. Currently, these systems are so incredibly fast that we can measure microscopic elastic strain with mind-blowing precision. But the future? We are moving straight toward dictionary indexing. Instead of relying on the Hough Transform to mathematically find those lines, AI will soon just compare raw, real-world patterns directly against libraries containing millions of simulated ones. This massive shift means we're soon going to be able to read heavily deformed, super complex samples that were previously considered completely impossible to index. It really leaves us wondering what previously invisible materials we'll be able to decode next. For PDF, check the description. Subscribe to the channel for quick and more updates.